Thanks for the introduction and welcome everybody to the presentation. I will speak about intermediate depth earthquakes in Northern Chile, as the title already says. And just as a brief intro, because not everybody in the room is a seismologist, in seismology we usually divide earthquakes very roughly into shallow, which is everything shallow in the 60 kilometers depth, deep, which is everything below about 350 kilometers, and the remainder, what is in between, is usually referred to as intermediate depth earthquakes. This graph here is a distribution of frequency of occurrence. So basically people took a global earthquake catalog, just looked at which depth appears how often, and this is here shown in a logarithmic scale. So you can easily see that shallow earthquakes are most frequent, because also they occur in a lot of different places, a lot of different fault zones all over the Earth's crust. Whereas intermediate depth and deep earthquakes are a lot more rare. And specifically important for us today, intermediate depth earthquakes on a global scale show an exponential decrease in frequency of occurrence with depth. Again, remember this is logarithmic, so a linear trend here would be exponential. However, these earthquakes are not unimportant from a petrological point of view in terms of processes that happen in the Earth. And also they can reach substantial sizes. Just last Sunday, we had a magnitude 8 earthquake in about 100 kilometer depth under northern Peru. So these occurrences happen. They usually don't get the big media attention because they're deep and thus don't usually cause many fatalities compared to shallow earthquakes. Intermediate depth earthquakes globally have been seen to form rather peculiar patterns that are called double seismic zones. An example of the first discovery of such a double seismic zone in northern Japan is shown here. But they've been seen in a lot of places, a lot of subduction zones around the world nowadays. And they consist of two parallel bands of earthquakes that are separated by about 20 to 35 kilometers. This is different between different subduction zones. And these 20 to 35 kilometers difference are completely aseismic, and you have earthquakes below and above. In a landmark study in 2003, some authors did numerical modeling of phase reactions within downgoing lithosphere. So they assumed a certain composition of the downgoing material and calculated which phases should be present at which area in the downgoing slab. And they found that the locations of intraslab earthquakes correspond pretty well to the regions where you would expect phase transformations or reactions to occur that set free water or fluids. And this solves possibly one big conundrum that has been in the community for a while. Because if you assume these deep earthquakes are the classical shear failure mechanism as we know happens along faults in the Earth's crust, they should not be able to occur simply because from a depth of maybe 60, 70 kilometers onwards, the confining pressures are so high that this should just not happen. Still, as you've seen on the page before, we get earthquakes all the way down to the bottom of the mantle transition zone, so to nearly 700 kilometers. And there was and still is a big debate how exactly these earthquakes originate, but nowadays most people agree that fluids that are bound in the crystal structure of certain minerals that then react and the fluids are set free, they are somehow connected to that. Whether the water then lubricates existing fault zones and allows earthquakes to happen, whether the pore fluid increase is responsible or some other mechanism is at work, this is still debated. There's a lot of different hypotheses there. So moving to the Northern Chilean case, why did I investigate this specific area? The first part of the answer has already given by Aleš. It's just very active in terms of earthquake generation, also at intermediate depth. The second reason is that GFZ Potsdam, along with several international partners, has been operating a rather large permanent seismic network in this area for a long time. The Northern Chile area, which is around here, so close to the northern border of Peru, has been identified as a long-standing seismic gap. So this is an area where a big subduction zone megathrust earthquake is overdue, or at least due. And this is why a lot of effort has been put into instrumenting this area. And this whole so-called IPOC network was started to be constructed in 2007, which means we now have more than 10 years of continuous data from this area. So what we did in a first step is to simply use not these 10 years, but 8 years of data in this case, and in an automated fashion create an earthquake catalog that encompasses a bit more than 100,000 events. The smallest ones go down to about a bit more than 100,000, yeah. And they go down to magnitudes of about 2 and the magnitude of completeness, so above which we should capture more or less everything within the network area is around 2.7, 2.8. Here you see these earthquakes plotted in map view, and the color refers to depth. So basically everything that is lightish color is relatively shallow. Here you have so this dark line here is the trench. So basically that's where the subducting plate is still at the surface, and then here you see the slab going down. And all this here is already at more than 100 kilometers depth. If we look at profiles through, so these 4 pink boxes correspond to the areas that were plotted here in east-west cross-sections. We see quite a lot of different interesting patterns. Also note that there are different colors at work here. I've already pre-selected certain populations of earthquakes and colored them accordingly. So everything that is pinkish here is probably in the upper plate, so in the continental South American plate. Everything that is in bluish color should be the plate interface, so that's where the downgoing Nazca plate is in direct contact with the South American plate and where they basically rub against each other. Then we see something that resembles what I've shown you before for the Japan case, which is this green and this red band here, which is this double seismic zone. So you have 2 bands of seismicity that in this case are separated by quite exactly 20 kilometers. But then we get something that definitely doesn't resemble the Japan case, and that is this really big and thick cluster down here at depth. Just to show you here the base or the reason why I colored the earthquakes as I did, this is simply a histogram of depth beneath the slab surface. So you basically sum up earthquakes going from the surface of the slab downwards. And here you simply see you have 3 clear peaks that correspond to plate interface, upper plane and lower plane. This cluster down here at depth is special not only in that it marks a prominent change of geometry compared to further updip, but it also shows a big difference in the seismicity rate. And I will try to visualize this here. So what you see here is again a histogram of earthquake occurrence with depths from the surface of the slab. And for this first plot, referred to as A here, I sum up the entire seismic zone starting from here all the way down to here where I put the first marker. And if we move on a bit further down and still a bit further, you will probably see that compared to the event numbers here on the left, that, remember, sum up everything along this whole gray bar direction extension, this area down here is a lot more active. It's about a factor of 10 more earthquakes in this cluster. And at the same time, we see that while in this plot B, we still see something of this two maxima pattern, even though the free space in between is filled up. Here in the red histogram, which corresponds to the further down dip portion of that big cluster, we don't see any maxima anymore. It seems to be rather homogeneously active. One last thing I want you to note from this image is that within this turquoise-shaped cluster, we also observe something like a kink in the slab. You will probably see this here. So the angle at which the subduction occurs seems to get steeper. This will be important in the discussion later on. So now I will show you an overlay plot of one of the east-west cross-sections of seismicity. Here now shown without the colors, just in black everything, with a few other observables or models from this area. First of all, I've plotted the bathymetry and topography over corresponding to the location here, of course, with vertical exaggeration. And here you can always see that the location of this strong cluster sits exactly where you go from relatively low altitudes up to the Andean Cordillera. If I then overlay a thermal model, these are isotherms from a model by Wada and Wang. You can probably also see that this here, so this change from the two seismicity planes into a very active cluster at depth seems to occur quite exactly where you get something like heat input into the slab. You can see that from the isotherms. Here you have rather homogeneous temperatures everywhere because you don't get in contact with the mantle. This comes more clear if we show the upper plate MOHO that is calculated from receiver function imagery. So here we have crust in contact with cold oceanic lithosphere that goes down, so temperatures are rather low. Here we start to be in contact with mantle, but still not much happens, and only from here onwards, for some reason, you get temperature input, as evidenced by these isotherms. And the reason becomes apparent here. I have to explain this a bit. This is an image of seismic P-wave attenuation. Attenuation means it's a propagation property. So basically, if we have high attenuation, we lose a lot of amplitude with distance. And conversely, if we have low attenuation, the waves propagate pretty well and don't lose much amplitude with distance, roughly speaking. Shown here in blue colors are areas of low attenuation, so where you have efficient wave propagation. Shown in red are areas of inefficient wave propagation. And usually, inefficient wave propagation is either due to fluids, the presence of fluids, or to high temperatures. So what we observe here is something that has been discussed rather frequently in literature, is a so-called cold nose of the mantle wedge. Everybody knows these images of the mantle wedge above a slab, and you're supposedly having some convection going on here. But in most subduction zones, due to the geometry, this convection does not, or the entire mantle wedge does not participate in this convection, but you have this so-called cold nose, which is the outermost extent of the mantle wedge that is usually left out of it for simple geometric reasons. So the convection would happen here, and this part basically just sits there and cools down over time. And we see very nicely that first, our transition between classical upper plane, lower plane geometry and this big cluster does not correspond to any isotherm. So whereas the earthquakes up here nicely follow the isotherm, so happen at rather constant temperature, this onset here clearly cuts across isotherms. So that you cannot claim that this happens at a constant temperature. At the same time, both the evidence from the isotherms and from the attenuation tomography basically shows that this here is quite exactly the point where you have heat input, or you start to have heat input when you move down along the slab. Next, I will show you a lot of focal mechanisms. So from the inversion of waveforms, you can deduce the basically the mechanics of the earthquake rupture. So basically, so which direction the stress field takes in the slab. I will, because these are way too many beach balls to be able to really see any trends in there. The total numbers are, I think, about 620 that we calculated. I will break everything down to these two rose plots, and you will see the azimuth and the dip angle of the t-axis, so the principal direction of extension. And we're starting with the big cluster here at depth. That's why that's the same color. And we can see here that this is a very nice and simple distribution with a maximum at around 90 degrees, so eastward direction, and a dip angle of about 25 degrees. In other words, this is very simple. This follows the slab down. The slab basically strikes, or the trench strikes north-south, which means the slab goes down towards the east direction, and 25 degrees is more or less the angle at which it subducts. So at this depth, we seem to have extension downwards along the slab, classical slab pool. That's not a big surprise. Next, I was curious if we see any dependency of these directions with where we are in this cluster from top to bottom. So that's what this plot is showing. So this arrow corresponds to this arrow here, going from the surface of the slab to the bottom of this cluster. And in these red colors, we now have this dip angle. In the black colors, we have this azimuth angle. And this blue curve simply shows how many earthquakes are there at each depth level. And the conclusion I would take from this plot is that, at least in those areas where we have enough earthquakes that statistics make sense, these two angles are remarkably stable. We have a bit of a wiggle here, but even that is only 6, 7, 8 degrees, so probably within uncertainty. So to conclude, this big cluster at depth seems to show very homogeneous down-dip extensive mechanisms, and that's it. Of course, now it's interesting. Oh, no, I forgot that. I just said this is very simple and obvious, but actually this comes as a bit of a surprise because most numerical models of downgoing slabs show something else in these depth areas. People usually assume that whereas the slab is bending up here because it needs to subduct down at these depths that we're in, 80, 90, 100 kilometers, the slab is actively unbending, so going from a curved geometry to a straight geometry again. And this should usually create a stress field that at least in the uppermost, maybe 10, 20 kilometers of the slab is compressive and not extensive. We clearly do not see that. Now moving to the other earthquake populations, we have a lot less earthquakes here that we can analyze simply because the area is less active. But for the red ones here, so the lower seismicity plane of the double seismic zone, we seem to get a rather similar distribution. There's a lot more scatter simply because we have less observations, but we also have a maximum that is roughly pointing towards the east and roughly in a dip angle of 25 degrees. So that's more or less the same here. The picture changes, however, when we go to this upper plane of earthquakes here. And maybe when you look at the dip distribution, you will already recognize that there's basically two different populations. One that seems to be something like these here, but then another one that is a lot steeper and apparently features more earthquakes. If you spend a lot of time staring at this map here, which is something I did and you don't have the time for now, you will realize that you can draw a line, something like this, through these mechanisms, and the result of that will be that more or less all earthquakes west of that line show compressive mechanisms, so thrust faulting, and all the earthquakes east of that line show normal faulting events or down-dip tensional events. And this is also visualized down here. This is the so-called Rake Angle, which simply describes the direction of movement on the fault plane, which jumps clearly from around plus 90 degrees, which is a classical thrust fault, to roughly minus 90 degrees, which is a classical normal fault. And if you spend some further time analyzing these earthquakes, you would see that this change over this line here corresponds very clearly to where the blue earthquakes, so where the plate interface ends down dip. And this makes a lot of sense, because the plate interface here is where both plates are in contact and you have mechanical friction happening, and that's why you get, in the blue zone, a lot of thrust events. And apparently this friction or this mechanical coupling extends into the downgoing slab, and also at these depths of 7, 8 kilometers below that plate interface, you still have the same stress field. However, as soon as we go from the plate interface here to a contact between downgoing slab and mantle, we change because we don't have the frictional regime anymore, and we again move into slab pull, which is the same as happening down here and also down here. So this was a lot of complicated information, but for us who are at the moment mostly interested in this transition down here, what happens when we go from these two planes to this big cluster, it means that directly at this transition, nothing happens in terms of mechanisms. They are down-dip extensional in both zones directly up-dip of this transition, and they are the same down-dip of this transition. So the stress field seems to be rather homogeneous. So to summarize the observations, before I come to some fancy arm-waving model, in Northern Chile, we see that from about 80 kilometers depth downwards inside the slab, we have a change in the geometry of earthquake occurrence, in that we don't follow isotherms anymore, but we have this massive cluster. At the same time, seismicity rate, so the number and also the moment release of these earthquakes increases quite drastically. Then we have a rather tightly defined cluster that extends to about 120, 130 kilometers depth. And in that cluster, the pre-existing gap between the two planes is completely filled up, but the cluster seems to retain more or less the spacing between these two planes. And this cluster has a very sudden vertical onset on the updip direction. That's what we saw, this onset that cut through all the isotherms, and also a rather sudden termination in the downdip direction. And that downdip termination in some areas coincides, in some areas is a bit downdip of an observable kink in the slab where it steepens. The earthquake mechanisms are uniformly downdip extensive, updip and downdip of this transition, even though in the upper plane, if we move even further updip, they change. I've shown you that before. And the onset of the unusual seismicity cluster seems to coincide with where we can infer heat input into the slab happening. We saw that from both the isotherms and the attenuation image. And possibly also with something like a maximum or an increase in slab pull forces. That would explain why the slab gets steeper. You basically pull more from below. So this leads us to this rather sorry hand-drawn cartoon that I will explain in a second. The conventional explanation for the lower plane earthquakes in subducting slabs is the dehydration of antigerite serpentinite. So basically you have water in the slab that is not just flowing around, but is in the crystal lattice of minerals. How this water gets in there is still somewhat debated, but most people think that you create deep cracks here in the outer rise where you bend the slab because it needs to go down, and water infiltrates and possibly gets as low as 20, 30, 40 kilometers beneath the surface. This leads to serpentinization of the peridotite rock there. So this is what is indicated with this, purple color, I guess. So this would be the area of the slab that is hydrated. It has some water in minerals. You cannot hydrate, however, below a certain point simply because of temperature, because at about 600 to 650 degrees, no matter what you do, this antigerite serpentinite will break down and you release the water. And conveniently, these lower plane earthquakes, as you've maybe seen a few slides before, follow this 600 to 650 degrees isotherm pretty nicely. So probably they are just an indicator of where this temperature is reached within the slab. And this also explains why at different subduction zones, the depth to this lower seismic plane is not always the same, because they have different temperature regimes. And when the slab is colder, you would have this zone a bit further down. When the slab is hotter, you would have it a bit further up. The upper plane of earthquakes, it is still very controversial whether that sits in the lowermost oceanic crust that goes down, or whether it sits in the very uppermost oceanic mantle. And there are different dehydration reactions for these two cases that people usually invoke. However, this is not really important to our discussion now, because down here we saw that we have a very sudden onset of a lot of seismicity, and that sudden onset seems to activate the whole volume. But this is important, so I will show you that again. Here, for example. You don't go further down than where the lower seismic plane was before. So if you extrapolate where these earthquakes are all the way down here, that's more or less your lower termination of the cluster. It does not go deeper into the mantle. So what we think is happening there is that you should have hydrated material all the way in here, and these earthquakes down here dehydrate at the critical temperature. So up here you have material that contains water but is at lower temperature and thus doesn't react. However, there are several recent papers from laboratory experiments where people have seen that antigerite dehydration can occur also at lower temperatures under certain conditions. These conditions include, and I think that's the most important part of these conditions, high stresses. So what we think is the following. We have something like a chain reaction going on. So here we have this whole hydrated material that is possibly something like metastable. And here, since you input temperature into the slab from above, you don't do that here because you're on the cold nose, you would maybe force at least some of this material to react. Not much of it, but some of it. And an important thing that I left out so far is that these phase changes, these dehydration reactions, lead to a higher density phase. So since they occur when you go down, you pack atoms more tightly and you get something that is denser than the material before. This means that when you here have additional reactions, you will densify parts of the slab, which creates more slab pull. The slab wants to go down. This creates higher stresses, which is a precondition for these reactions to occur at lower temperatures. So you will have some more reactions occurring. This will create more high density material. You increase the stress again and so on. This is something like a runaway process. And if this hypothesis, and that's all that is at the moment, is true, then this would lead to a big burst of reactions happening here. And at some point, going down dip, you would simply run out of water in the slab, and that's where the earthquakes terminate again. And the slab steepening would basically show that you create the denser material at this spot, and that's why you have this kink. Now, this is a very fancy hypothetical model that was just put together for one subduction zone in the Earth, but of course, at least the composition of slabs should be more or less similar around different subduction zones in the world. So it would be very strange if it only occurs in Northern Chile and nowhere else. We definitely know it doesn't occur in Japan. I've shown you the images before. Japan has these nice two plains that just go on for quite a distance down dip and then at some point end. Japan doesn't have this big cluster at depth. So I was searching through the literature whether I could find any other places in the world that might show similar behavior. I found two. This is an image from the Alaskan subduction zone, and this is an image from the North Island of New Zealand, where you appear to see something somewhat similar. The problem with looking through literature is that most areas don't have the same resolution in earthquake locations. So not often can you actually clearly discriminate between upper and lower plane and then where it ends. But in both these cases, you seem to have an increase of event rate with depth and a somewhat thicker seismic zone. But this exercise was somewhat unsatisfying for me. So I went on to rather use a global catalog. And since I just said that location precision is not enough, what I did is simply I took a total of about 60 subduction zone segments, and I did a simple histogram of event depth in these subduction zones. Here you see the Northern Chile case, where you very clearly have a big maximum at around 100 kilometers depth. That's this cluster I've shown you before. And we know from the first page of my presentation that in the global average, we should not see this because the global average clearly shows that event numbers go down with depth. So this I did for all these different segments, and I basically gave a red color wherever I don't see such a maximum and a green color where I see it. Here's other examples being shown. I never saw such a clear maximum as in Northern Chile anywhere, with the exception of Alaska. This is not this one here, but actually the one east of it. This is also very clear. There's some areas like the Alaskan Peninsula, like Bali, Lombok, that show something of a maximum here, but most areas don't. Most areas just show this kind of normal decline here. I then went on to try to correlate the places where I see this kind of pattern with slab parameters, like dip angle, like lithospheric age of the downgoing slab, but couldn't find anything. So my current hypothesis is that it doesn't depend on any of these parameters, but rather on something like hydration state, something like lithospheric, how do you say? Yeah, structure, roughly speaking. I can't think of the right word now. So something that is not easily cataloged in any of the available studies, but this will have to be investigated more in the future. So this is where the scientific presentation more or less ends. However, this is also something like a presentation of myself to the whole institute, because I just started working here. So in the following slides, I put together a few of the things I'm currently working on so that people roughly know who I am and what I do. So I did a bit of a brainstorm and came up with 4 to 5 things that I'm currently working on. 4 of them, and those are the 4 that are active at the moment, all somehow based in Chile. And the 5th one is a project we applied for but are waiting for whether we get the funding or not. So the first project I'm looking at is with collaborators in Chile, not looking at these deep earthquakes now, but looking at earthquakes on the subduction interface, so where the 2 plates slide past each other. And it's a very well-known concept that on this subduction interface, you have so-called asperities. So areas of, for some reason, higher frictional strength, and these areas correspond to where the big earthquakes usually occur. So they are here depicted by these darkish chunks that are surrounded by areas that are more freely slipping and thus don't have such a high friction. And the reason why we got into looking at megathrust earthquakes in central Chile now is that I also did an earthquake catalog for that area. And this is shown here. And when you only look at events on the plate interface, which is what is shown here, and you sit down and look at this plot for a long time, you might see that you see kind of 3 half ellipses or something like that outlined by the earthquakes. And very interestingly, these 2 lines here, they are the slip contour lines of the 2015 magnitude 8.3 ERPEL earthquake. And that earthquake fits exactly within that northernmost ellipse. So at the moment, we're not completely certain if this is something or whether that's just coincidence, but it might be that small earthquakes on the plate interface basically outline where you have these asperities that might create the next big earthquake. And in order to find out if this is actually a true correlation or this is just coincidence, we are currently working on trying to compare this evidence with geodetic evidence. This is a logging map from GPS data, where basically people see how much of the plate convergence translates into deformation of the upper plate. But if this is the case, there is already a study that shows a physical model for it. That's in Moreno et al. Last year, where they simply assumed to have an asperity that has higher interplate locking than other areas and ran that through a mechanical model. And that model shows that with time, this asperity leads to a stress concentration along its down dip end. So this is an observation that fits pretty well to what the earthquakes seem to define. So maybe these little earthquakes that form these ellipses are just the signature of a process like this that has so far not really been seen. Secondly, we plan to extend the first study, so the one that I've presented in detail and the one I've just shown you a glimpse of, to the entire Chilean margin. Not sure if this is visible, but these here are the stations I used for the study I just presented you. And these are the ones for which I now just downloaded data. And the idea is to see if we can see any along strike variations, because one of the special things about the Chilean subduction zone is that you have a lot of features on the ocean floor that come in and get subducted. Like down here you subduct mid-oceanic ridge. You have several seamount change and hotspot chains that enter the subduction zone, so those should have an influence on the behavior, both at depth and on the plate interface. Thirdly, this is also somewhat related. There are a lot of people that think these intermediate depth earthquakes in the true plains are related to bending. And what I've shown you also shows a relation of these earthquakes to bending, but in my coordinate system, the bending happens because of the earthquakes and not the other way around. A lot of people, however, assume that you have at the trench, you extend the plate at the top. That's why water can come in. And then when you go down here, you unbend the plate again and you basically do the opposite. And that means you extend the plate further down, and that's why water would be pressed out of there. However, one of the problems with that is that this means you should see a stress field that is compressive in the upper part and extensive in the lower part down here. And as I've shown you with the beach balls before, at least for Northern Chile, I don't see that. Moreover, the geometry of the slab in models like this is very idealized. And here, this is the slab surface are calculated from the Northern Chilean data. And the red and the blue basically shows opposing curvature, like bending upwards and bending downwards. And this clearly shows that it's a lot more complicated than the simple cartoon. So maybe these models need to be somehow at least adapted. And this is what I'm working on with Tim John at Freie University at Berlin. And lastly, there's a guy at GEOMAR in Kiel, Jakob Gersen, who approached the last AGU. And he had the idea of investigating bathymetry data. GEOMAR does a lot of marine data acquisition. To correlate bathymetry data from the area of the downgoing plate with earthquake occurrence. So the idea is that if we have, I didn't really go into detail there, but we also see a lot of variation of earthquake occurrence if we move north-south along the study area. So in the very north, we don't really see many earthquakes at deeper depth in the slab, whereas further south you do. And one possible reason for that would be that simply here you have less water in the slab and maybe it doesn't go down far enough to reach this isotherm. The amount of water you have in the slab should be related to the amount of faults of structures you have where the plate bends in the outer rise. So the idea is to map out features in the bathymetry offshore, see if there's any along strike variation of number and offset of these faults, and correlate that with earthquake occurrence with depth somehow. And if there's a correlation, then it would maybe mean, okay, if we get more pervasive faulting of the oceanic plate, we get more water in, and then more water leads to more earthquakes at deeper depth. But this is really just a plan at the moment. This is not something we just started. And lastly, in April, we, and that means quite a few people from the geodynamics group here and myself, applied for a joint Czech-German project that is concerned with another subduction zone now. This is in Indonesia, in the Lesser Sunda Arc. And we plan to put up some seismic stations at an active volcano there and use both volcanic earthquakes and also tectonic earthquakes at depth to further image the plumbing system of that volcano. So we will know whether that gets funded or not in late November, I think. And yeah, that's everything I wanted to show. Thanks a lot for your attention.
Thank you very much for your great presentation. So open to questions, comments.
Your evidence of double zone was very impressive. You also mentioned global catalogs, but I would like to ask you in more detail. Do you try especially for your zone to use only global data catalogs and to see whether there is doubling or not? Or can you say that using magnitudes larger than 3, you do not see this doubling in global catalog?
When you plot the global catalogs for that area, you have difficulty seeing it. But I think that is not due to the fact that the larger magnitude earthquakes don't show it. It's rather a location precision issue. So I think in global catalogs, the depth resolution of earthquake locations is usually just not sufficient to really resolve those two planes. So you just get something like a cloud. What you can see in global catalogs is what I've shown, that you get more earthquakes at these depths of between 80 and 120 kilometers. That you can see. But the double seismic zone is not really resolved. So.
Okay, and a related question, why are you able to see this doubling? So is it just the density of your network or some special location method? You did not mention it. Is it hypo-3D or something like that?
It's
1D model, 3D model. Could you comment a bit more about the location procedure?
I didn't say that because not the whole audience is seismologists, so I didn't want to go into that so much. It's an automated procedure, but the last step in that procedure is double difference relocation, yes. And I'm using, in the last step, a 2.5D model. So I use a 2D model that I just stretch along the strike of the slab. I think that the location precision mostly comes from simple geometry. So if you have many local stations, you get a lot more resolution than when you use global data. That's no surprise. And of course, a relative technique like hypo-DD benefits a lot from the amount of earthquakes. So if you just have a few tens or hundreds of earthquakes, you don't gain so much from a technique like that. But if you have many tens of thousands, then basically that method does a relative relocation based on travel time differences. So you can imagine if the event cloud is denser, then your precision also gets higher.
And S-waves are included, yes?
S-waves are included, yes. Yep.
Can you comment on what is the correlation between your very different zones of seismicity and vertical displacements recorded by deviates? Is there any, or?
I wouldn't think so, because at this depth, you basically have the slab in contact with the mantle above. So I don't think that processes at this depth really translate much into deformation of the crust, because you have something like a viscous layer in between that decouples the two. However, I don't think I have an image of that here now. There could be.
Image of displacements, are there any?
Yeah, I mean you do get displacements, but those are simple from the relative motion along the plate interface. So of course, you have a convergence rate of about 7 centimeters per year in this area. You have the Nazca plate moving in and then rubbing along the plate interface, and that means that the vertical motion along most of the subduction zones is upwards simply because you buckle up the plate. And this is not homogeneous, but that is mostly ascribed to different proportions of or different amounts of friction along strike. So in some areas, you translate all of the incoming velocity into deformation of the upper plate. In some areas, you only translate a proportion of it. But I don't think it's really much related to the processes at depth.
I'm just wondering, your earthquakes in Chile that you observe, they are like different driving mechanism or loading mechanism or whatever, why they appear, why they are there. And so I'm wondering whether there are also like other characteristics of these earthquakes that distinguish these different clusters, like maximum magnitude, p-value, Gutenberg Richter, stress drops, or things like that. Did you look at those values, or
some of them? Some of them. We looked at p-values. P-values seem to be quite a bit higher in that deep cluster compared to further updip. We're not sure what that means, but that's an observation. We've looked a bit into properties like aftershock productivity. Also there seem to be differences, like these deep earthquakes have a tendency to get aftershocks, but a lot weaker than shallow earthquakes. We have not investigated stress drops yet. That is something that could be done. But yeah, it definitely makes sense to try different techniques to find out whether there's any substantial differences between these different populations. Yeah, I think that's, at the moment, that's still in the works. Yep.
these asperities that you somehow mapped by means of earthquake occurrence. So now you know what they are, and maybe these are the zones of some future big events. So you are going to make comparison of the occurrence of earthquakes there in some 1 year interval or so.
Well, not completely sure yet. Just go back to this one here. What is important to know here is that directly south of here, so starting from there going all the way south, is where the 2010 Maule earthquake happened. So these two maybe asperities are basically the gap between Maule and this Seismically earthquake that happened in 2015. However, the question with something like this is always, does this really tell me that the maximum earthquake size here is going to be this? Or can they still jump over this gap and both go off at the same time? I would not exclude that possibility. And that leaves the maximum possible scenario as what people have known before, because people knew before that this is the size of the gap between those two earthquakes that already happened. So maybe the conclusion in terms of what to do is, yeah, somewhat trivial. But still, if this is something that works in other areas as well, it's something that has a high potential. I'm not sure how exactly we are going to investigate that, because the problem is, compared to the study I've shown in the beginning, event numbers here in the plate interface are not so high. So what I'm showing here are actually 4 years, and I'm not sure if you would see the patterns you want to see in only 1 year of data. Maybe you would, but you need a bit of fantasy, which is not what you want to use.
Okay.